I'd like to welcome everybody. My name is Chris Riola, and I'd like to introduce my colleague and friend, Peter Keep. Peter's been teaching at Morraine Valley Community College in Palos Hills, Illinois since 2015. He has a master's degree in mathematics from Eastern Illinois University and is finishing a master's degree in applied statistics from Colorado State University, expecting a finish in June. During the 2020 work from home saga, he enjoyed live streaming math content to the students and the general public on Twitch. He enjoys using technology to help students engage deeply with mathematics concepts and applications. So with that, I'd like to turn the floor over to Peter. Enjoy.
All right, can you all see this?
Yes.
All right, cool. Thanks, Chris. Chris Riola is going to keep an eye on the chat, but with so few people here, I expect that I'll be able to see what's going on there too. So if you have questions, just drop them in there and I'll stop and talk about them. Here's some links. I'm going to put these in the chat. If you want to follow along with the slides, there's a link to the slides. And then I've got a couple more links that I'll drop when they're relevant. And yeah, we're going to talk about kind of my experiences with using the programming labs in calculus. So first, what are we really doing? What are the goals of the talk? What are the points that we're going to try and talk about here? First, we're going to just talk about what I'm doing in my calculus classes right now with these labs, some of the structure and some of the kind of ways that I'm building all this stuff. We'll talk about some of the reasons that I'm doing it. What are the motivations? Some of them are pretty obvious and some of them maybe aren't, I don't know. And then we'll try and figure out if, the labs have worked, whatever that means. I also have some examples that we can kind of try together. The stuff that I'm going to be using is built into the Google Drive ecosystem stuff. So they're super collaboratory and things like that. So I'll share a link for some examples that we can go through together just so you can get a feel for like some types of things that I'm doing. And then at the end, we'll finish it up with just trying to figure out like, what are some overarching things that I've learned? What are some things that I'm thinking about changing? That kind of stuff. So we'll start off with just what am I even doing here? So this is how I'm structuring the labs. Each lab assignment starts with a quick overview of some of the topics that I'm covering in the lab. I'm just trying to give students a really clear idea of what specifically they're going to be thinking about and doing, and maybe even how those topics connect to kind of the overall picture of the course. So I normally have some introductory stuff. And then I also will include some basics about what kind of code we're going to be using in the lab. They're really unfamiliar with computer programming. Most of them come in with zero experience on writing computer code. And so I just try and give them some small introductions of like, hey, we're going to be using this sum function, and this might be how it works. I try and pepper that throughout the lab. It's not always right at the beginning, but try and give them a lot of commentary on the types of code and also commentary on the types of examples that we're going to be doing. Whether we're looking at, looking at limits graphically or playing with Riemann sums or something like that, I normally will introduce several examples of almost exactly the types of things that they're going to be doing. With my Calc 2 classes, I give a little bit more flexibility for myself to deviate from those examples. So sometimes I'll show them an example of something, and then in the tasks that they have to do, it'll be a little bit unrelated. But they should still have the tools to be able to do all that stuff. Then I just give them the actual tasks to complete. Afterwards, after each thing that they do or each group of things that they do, I try and have some kind of follow-up questions just to get them thinking about, what process did you actually complete? How does this connect to the class? Maybe think about their thinking, get a little bit of metacognition in there, stuff like that. These are some of the topics that we cover. I started small when I built these, and so I'm continually adding to this whenever I'm thinking it's appropriate. I do this for single variable calculus, so Calc 1 and 2. For both of my courses, I started off with an introductory lab that has zero calculus content on it. It's just to get their feet wet with the style of these things, the labs, the kind of structure of it, a little bit of the programming code. So I'll, show them how to add two numbers, how to multiply, how to use exponents, how to bring in some trig functions, and how to even build their own functions in there, how to graph things, stuff like that. So that when we get to the calculus, they can focus on the calculus side of things instead of wrangling code so much. For the actual calculus topics, I do a lot of limit approximations, whether that's looking at graphs or doing some numerical approximations with limits. Newton's method is a really great thing to do with a programming language for obvious reasons. It's super computational. Riemann sums for approximating integrals are really nice. I use that in Calc 1 and in Calc 2 when we talk about volumes and arc lengths and all that kind of stuff. Improper integrals I recently added into my Calc 2 labs, and that's been a lot of fun because an improper integral is a limit. It's really nice to go back and do some more like limit approximation with those improper integrals. I talk about sequences and series, Taylor series, show a little bit of parametric and polar graphing. That one is new this semester too. So I haven't exactly seen how that's gone over with students, but I think it's going to be pretty good. So there's a decent amount of topics that I've got, and hopefully I'll be able to add more. This is kind of the basics of what these are going to look like. So all the code is written in Python, which is a programming language. If you didn't know, it's a relatively easy one in terms of the syntax to learn. The way that you write it isn't too bad. And then I use Google Colab. It's their collaboratory thing. It's a Jupyter notebook. So if you've done any sort of computer coding before, you might know what that is. But I'll show you what it looks like in a bit. Essentially, it looks like a notebook where it's got a mixture of text that you can format with like Markdown. It's got LaTeX. You can include notation and math stuff in there. And then it'll have little chunks of code that you can run and it'll display outputs. It's really nice because it's built right into Google Drive. So it's portable. I don't have to walk students through downloading anything. That was a big deal for me because I don't work in computer science stuff at all. I don't know a lot of the ins and outs of like how I get a working Python installation on a student's computer, what kind of like code editor to be giving them, things like that. This is all built in and no downloads or installation necessary, which is great. And then the other thing that I'd like to explore a little bit more is how collaborative Google Drive and their kind of ecosystem is. I know how it works with Google Docs and Sheets and stuff like that, but I want to play a little bit more with these coding notebooks and maybe experiment with bigger lab assignments for small groups to work in, and they can work collaboratively on that. This is what it looks like. I've got a little video clip of me just kind of like scrolling through it so you can see. So again, you're going to see a mixture of text that's formatted, some notation on there, and then some code chunks. So this is what it looks like. I'll kind of talk as it's going. So here I'm importing some code libraries. You can see I'm introducing how we're going to look at improper integrals. In this, I'm just going to run a little picture of a graph. It's not a very helpful graph. I try and explain a little bit why that's not super helpful. So I do a different version of the graph that they can see. And again, these are just examples that I've written out for them. So they literally are just clicking that little play button and it's running the code. And in this case, it's going to spit out a Riemann sum approximation of that improper integral, which I think is pretty cool. So these are the examples that I build. And then later on in the labs, I'll have blank code boxes for students to do the same kinds of tasks with some instructions on how that goes. I can show this again if you want. But again, I think it looks pretty nice. If you look at the integral, you'll notice that like, oh, this is something that a student could do by hand using integration by parts. And so at the end, when you see the numerical approximation of this, I think it's like 0.50000000 something, whatever. And we do a pretty good job. And it's nice because we can talk about like how we can get better approximations out of this by either making our delta x smaller on our Riemann sum, or this end limit of integration is just a really big number that's trying to approximate infinity. So we have all these little discussions that I can include in the follow-up questions for students to think about. So that's this general structure of what I'm doing. But maybe more important or just as important, I don't know, is like, why am I doing any of this? There's a whole bunch of reasons. The first and obvious one is academic integrity. In March of last year, when we went online, I, like pretty much everybody else that I know, had just a flood of cheating in my classes. And it was super frustrating to deal with. I'm very over filling out the academic dishonesty forms on my institution. And so I tried to find a bit of a solution for that. One of the best parts about these labs is that students can't just copy and paste this into Chegg and get answers, because I built these myself and I don't know any other calculus classes that are doing the same kinds of tasks as I am. There are people doing labs in Python, but there's not a ton of people doing it. And the tasks that we're doing are just variable, right? We're all just making our own kind of specifics up. So they can't just copy and paste. They also, kind of on this, but less of an academic integrity thing, they really can't get a lot of help from anyone other than me. And so it forces me to be really available to students, which is a good thing and sometimes a bad thing for my own schedule. But I think they're learning that I am maybe a better resource for them than something like Chegg. And I'm hoping that that spills over into other things that we do in my class that they might normally kind of go to something like Chegg for. Students also have to tell me their thought process, right? The way that I'm asking follow-up questions, it's really easy to just have them dig into some of that stuff and think about it. And then, like I said, collaboration is okay. I work with students on these. I don't expect them to know much about the coding stuff. And so I help them with that. And I let them know upfront, like, I'm going to be okay helping you with the coding and you can get help from each other with that. I want you to complete the tasks and then respond to them later. And so they've done a pretty good job of working together in an appropriate way on the code and not working together when they're supposed to interpret what they're doing, or at least giving their own thought process on there. Another one outside of just cheating is equity in my grading practices. I'm trying lately to move away from just using a few high stakes exams for grading in my class. I've known for a while, but I'm realizing more and more that those kinds of grading practices don't fit well with the style of class that I'm trying to create. And I don't think that they're super equitable for students. I also like that there's no invasive proctoring software needed. I am super anti honor lock, proctorio, anything like that from an equity standpoint. And so I really like that this is another kind of assessment where I don't have to use that. It doesn't seem appropriate to even use that in this case. There's a lot of diversity in the types of assessments that I have now in my class, or at least maybe more diversity in the types of assessments that I have, in the ways that I can ask students to think about topics in the course. And I think I do a better job and a more equitable job of figuring out what students know and what they don't. And then the big one for me is that this is going to be super easy to plug into a mastery grading or like a standards-based grading setup. And that's what I'm going to be moving towards. I have been moving towards that. I'm almost there. And this will be really easy to map these lab outcomes or lab topics to outcomes in the course and just plug in there. I'm also interested in moving towards some sort of like a portfolio approach to grading in my classes. I don't know if that's really speaking so much to equity and grading and stuff like that, but it's something that was interesting, so I put it on here. I know a lot of writing classes will do things like this, where at the end of the semester or at different points in the semester, they present a portfolio to an instructor, and that's kind of what they get graded on, where students can kind of select what goes in there and work on it and revise it. And I think that would be really interesting to do. I have no ideas really on how that might get implemented here, but I feel like these could work towards that in some classes. Another reason that I'm doing it is that I think it creates a valuable experience for students. Introducing students to computational software is a good thing, I think, in calculus classes. I know that a lot of places will use things like MATLAB, Mathematica, or Maple, and I'm not doing that. I'm using Python, which is a little bit more general. I say that's not always a good thing, but sometimes it is. I've found that my engineering students that come through my calculus classes, I can kind of expect that they're probably going to use MATLAB later on in whatever other kind of engineering specific courses they look at. So maybe it might help them to see MATLAB earlier, but I'm seeing more and more of statistics students and data science students and things like that, where in their future, they're not probably going to use any of those specific computational softwares. They're probably going to deal more with just a general programming language like Python or R for statistics or something like that. So I think it's helpful to be a little bit more general. There is a bit of problem there where that can kind of cause the labs to blow up and become a big project for me instead of having something that's kind of self-contained in MATLAB or Mathematica or Maple. Those softwares have such good solutions for the kinds of questions that I'm asking in calculus and in other courses, kind of pre-built methods and things like that, which would be really nice. Python doesn't always have that, which is sometimes frustrating, but a little bit of Googling around has helped me kind of fix that. I like that students are getting experience seeing some problems that aren't just kind of clean, nice problems from a textbook. I I'm trying to give students, integrals that they can't actually anti-differentiate nicely. Things that maybe don't have an elementary antiderivative, like sine of x squared. I'm giving that to my Calc 1 students because they can use a Riemann sum to get a really, really, really good approximation of a definite integral for a function like that. I like to look at the gamma function with my Calc 2 students when we're looking at improper integrals and kind of play with those. And those are things that they wouldn't normally see in some of their homework problems, but they get to kind of play with and sink their fingers into. And then students also are starting to see some of the broad themes that I do a poor job sometimes of showing. Calc 1 isn't such a big deal for this because I think it has such a nice story, right? You start off with limits and you build towards continuity, and then continuity kind of informs the rest of the course. You talk about the derivative and how you interpret all that. You get all these big concepts that just basically fall out from the intermediate value theorem and differentiability. And then after that, you look at antiderivatives, which seems to be a natural step. In Calc 2, it seems like the topics are a lot more jumbled. There are some nice themes in that class, but I don't do as good of a job of showing the story of that class. And so I'm using the labs to try and connect topics. And I think students are starting to see some of those more broad themes in the course. I also have a list of super selfish reasons. When I started this, I wanted to get better at writing code. And so I thought like, hey, I'll make my students do this and I'll grade it and I'll have to create assignments and that will motivate me to learn how to do this. The kind of coding that I'm writing is not so computer sciencey coding because everything is through a math lens here. But it's still been fun to get better at this kind of thing. I also was really bored with the types of questions I was asking students, and I didn't have a ton of motivation to just write new ones. And so I thought putting myself in this different context might get me to ask students more interesting questions. In March and April and May of last year, I was burning out really quickly with just teaching online. And so I thought this might be a fun project to kind of capture my attention a little bit. And it worked a little bit. And then I also was so tired of writing online exams. So those are some selfish reasons of why I wanted to do this. The big question, I think, is, has it worked? I've been doing this for almost a year now. How can I reflect on this? Has it been successful? I think we probably should stop and think about what that really even means. When we talk about using labs in a calculus class, if it's worked, we really need to know who are we asking here and what do we think worked means and what do they think worked means, really. So I have a couple of options for what we think worked might mean. Have grades improved? If grades have improved, maybe we can check the box and say, yes, labs have worked. And my answer to that is I kind of don't really care for a lot of reasons, but partly I'm shifting away from traditional grading practices anyways as I'm implementing these labs, but also I started them during a global pandemic where grades were like super volatile. They were all over the place. And so I don't really care so much to compare to a baseline there. And I think I'm still in a little bit emergency mode with my grading stuff. Here are a couple of things that I found interesting in the last year. The first is a link to a talk by a professor out in Utah, Spencer Bagley, on ungrading. And that's been really enlightening for me. And then maybe you know about Francis Su. There's 7 exam questions for a pandemic that kind of touch on what I'm thinking here. This is a whole other talk, though, that I'm not near qualified enough to give, but I kind of don't care about comparing grades for my classes before I was doing this and after doing this. So a different way of trying to understand if this has been successful or not is trying to see if students understand the course concepts better. Hopefully that actually is the same thing as our grades better, but maybe this is a better version of that, right? Because if students understand the course concepts better, then grades will improve if I'm doing my job right in terms of assessment. And this one is hard still. I think they are, but I don't have a good baseline to compare to because the way that I was grading things before, you can say pre-pandemic, I guess, I don't know if I had a really great idea on how well students understood specific course concepts in my classes. I think I did a pretty good job of understanding or knowing if a student had an overall sense of understanding for the course. So I think my end letter grades probably did an okay job of reflecting like, yes, this student really understands the general idea of what Calc 1 is and all the stuff in here. But when we get a little bit more granular to specific course concepts, I don't think I really had a good idea of what students knew and what they didn't. Again, this is kind of a plug for my transition to mastery grading. There's a conference coming up in June. If you're interested, there's a link. I'm planning on using that as some motivation to switch most of my classes over to some of the mastery setup so that I will have a better job of knowing how well students understand specific course concepts. So, okay, we could figure out if I have a better view of what students understand, and I think that's absolutely true. I do. The labs have been like an oral assessment, which I've been wanting to do anyways. And that's because the process is super interactive. I'm the one that they come to for help. And they talk with each other about all this stuff in my little like class chats. And so I can see exactly the things that they're struggling with, whether they're asking me or each other, because there's not really any outside sources that they can turn to ask those questions. I also have tried to make my follow-up questions, the things that they're responding to, pretty chatty so that they have to write and kind of talk about what they're thinking. And so I feel like I get a really good glimpse into how they're approaching all this stuff. And then also the labs cover a bunch of topics. Like I said, I'm trying to connect some themes in the classes and stuff like that. And so it's really easy to see like what students are really seeing the underlying themes in the course and which students maybe aren't, and which connections are students able to make and which ones aren't they able to make. So I do feel like I have a much better view of what students actually know in my classes than I did beforehand. But like I said, I don't think I had a very good view of that beforehand at a granular level. Probably the last way of measuring success of these labs is if students think they're valuable, right? That might be an important thing. This is something that I made for my students because it pretty honestly reflects their experience with taking labs. They start off with not liking them. Get that thing out of my face. And then they take a little bit of a bite from one. And then by the end of the semester, this is where they're at. They're at this nice little happy, lovey bird. Not all of them, but I think in general, students are pretty terrified of these near the beginning of the semester. And it does take a lot of careful attention to make sure that students can come to see that they are valuable. I have two student quotes here. I bolded stuff in here that I thought would be interesting. You can read this on your own, but I'm going to point out a couple of things. I like this. When I first saw that we had labs in this class, I was terrified and annoyed. I didn't understand how labs would help me do calculus in any way. I mean, like, that's kind of the mentality that I found. Students come in and they're like, wait a second, I'm not a computer science major. Why am I doing this? And so that takes a lot of work on my end to first kind of ease that anxiety, and second, try and build assignments that demonstrate for themselves that these are helpful. I want students to come out of these knowing like, oh, okay, I actually did get a lot out of this. And this person kind of gets it, right? The labs help me understand the material in a better way than any test could ever. I like that because it's also framing it on the fact that like, these are learning experiences. This is a formative thing, right? This is not like this student has experienced tests before where a test is strictly, what do you know now? These labs, at least in this student's mind, are helping them learn the material as they're taking it, which is great for me. I feel like I'm doing my job okay. And then at the end, right, they focus on the fact that the labs tie the material together, which again is like a really big point that I've been trying to make. Here's another quote from a different student. And again, in all honesty, at first they seem scary because I never did anything like this before, right? And I think that's the main reason that students have been scared of these. It's not because anything about the way that I've written the labs or any of the specifics on them. It's just the fact that these are new experiences for students in an already scary class. Calc 1 or 2, those are classes that a lot of my students come in nervous about anyways. And so they start doing this type of thing that they've never done before, and it can feel really disconcerting. And again, okay, reading through it helps understand what we've done a little bit easier. So can we try this together? Can I show you what we're doing here? I have a link on the slides, but I also have a link that I'll just post in the chat. Hopefully this works. If you click on that, you should see this. So I'll just kind of show you how this works. This is just a truncated set of examples. And if you want to see more of these, or you want to see some more explanation, there's a link to just all the labs that I've written for my Calc 1 and 2 classes. And specifically, you can see what I call Lab 0, that introductory lab. That goes a lot more in detail, I think, into like how the programming language is used. So all I wanted for this is for it to just be kind of like a couple of examples of some cool things to do. So anyways, we got to run this code chunk first. This is NumPy or NumPy, which is a Python library. It's basically just a bunch of pre-written code that's going to allow us to use things like trig functions and exponentials. We're going to prefix it with NP. So anytime you see NP in our code later on, all that means is that we're calling this from this pre-written library. And then the same thing, we're going to use matplotlib, which I think is the same kind of code that you would use for plotting things in MATLAB, but I don't really know. That's going to be for our graphs. And so you're going to see a lot of PLT kind of prefixing things from there. No big deal, but if you're following along, just make sure you run that or else you're going to get errors. We can take a look at some sequences and series here. I think that works out really well. And then we'll move over to limits after that. Limits and sequences are kind of the same thing, at least in the examples that I have, but it'll demonstrate a bit of the difference between the way that the graphs are going to work. And then we'll do some integration. And if we have time, we can look at some Newton's method, but all of this stuff you can play with on your own if you want to. So I'm giving my students this sequence that we're going to look at. I give them the explicit formula for the terms. Maybe we want to take a look at the picture of it and do some guesses on whether this sequence is going to converge or diverge. I say that this one is maybe a hard one to find the limit by hand. It's not that hard. You just use the squeeze theorem. But for Calc 2 students coming into sequences, they probably haven't done limits for a little bit. And I know that my Calc students in 1 or 2 hate the squeeze theorem for whatever reason. So we'll just run this chunk of code, and all that's doing is defining this A function that's going to define my terms. So you can see np.sine, that's just from the sine function coming from that NumPy package. Double asterisks are exponents. So this is n squared here, which is kind of silly, I think, but whatever, that's just a Python thing. So n sine of n over n squared plus 1. They hate the squeeze theorem because they can't follow the mindless computational algorithm. I don't disagree with that, Chris. That's probably a good point to make. Here's the graph of it. So I'm just going to set a list of indices. This is again coming from NumPy or NumPy. This is a nice way of building up a list of numbers. There are other ways of doing this in Python, but this is the one that I use. This is going to basically just count from 1 to 500, but note the way that this function is built, it counts up to but not including 500. Later on, we'll be able to add a third argument to this that's going to count as like a step size. So if we leave that blank, it's going to default to counting by ones, which is great for us with sequences. That's what we want to do. And now you can see I'm plotting this stuff. I'm going to plot my inputs on the x-axis. That's that list of indices. My outputs are the A function evaluated there. And then this just says I'm going to use a dot for my plotting character for the actual points. I can change this to a couple of different things. Like if I make it an O, it's going to make them bigger points. If you make them a comma, it's going to be small points. You can probably barely see that on my screen. And if you take it out completely, then it just is going to connect the dots. I'm going to bring this down to, so it's only going to have 4 points on it, and I'll run this again and I'll show you what it's doing. So this is how things get graphed normally. And you can see why this is a problem for sequences. So that's why I'm just going to say, okay, plot it with the actual points. Now, instead of connecting the dots, we'll be able to see the actual points. But let's go back and put this to like 500 or I guess 499. Hopefully my students would be able to look at this and say, oh, this sequence obviously converges, and specifically it's going to converge to 0, right? Or at least something very, very close to 0 if it's being tricky. But they probably have enough intuition by just looking at the degree on the bottom and the fact that sine is going to be bounded between -1 and 1. It's not really going to grow n any much or any bigger. So they probably already have the intuition that this is going to converge to 0. And this is just a nice confirmation. I'm going to add a horizontal line here. Maybe you can see that on my screen, maybe not. I can zoom in if you want a little bit more. But I'll just add a horizontal line here at 0. This is like my guess. I'm adding a horizontal line at 0. It's going to span from an input of 1 to 500. I guess I probably could have put 499 there, but you can't tell the difference. It's going to be red, it's going to be dashed, and then this Z order thing is just the order in which The lines get stacked on top of each other. No big deal there. And then we can show it. We can print a numerical approximation of this. So what this is doing is it's taking this -1 here, is saying, what was the last value? We'll count from the end of that list of indices, and we'll count 1 from the end. What was the last index that we used? So this is 499, and plug that into your sequence. What term was that? What's the 499th term? That was the last one that we plotted. It's 0.00098. So hopefully by looking at the picture of the graph and getting this, they can see like, oh yeah, these terms are going to 0. And if they're not sure, the great thing about this is that they can go back here. They can take this list of indices and they can just add a couple zeros and say, all right, let's go up to 49,999. We'll run this again. So now you can see our graph doesn't look very interesting. And I'm just going to skip down to the numerical approximation. This is negative 0.0000105, right? It's times 10 to the -5 here. So hopefully they're able to see that, like, okay, yes, this sequence is converging to 0. We could ask them some follow-up questions on what that tells us about a series using those same terms. Not much, although it doesn't obviously diverge from the divergence test, right? Or they could say, oh, maybe this is like going to be alternating and the terms go to 0. And so maybe the alternating series test says that it does converge. It's not actually alternating, but oh well. We can take a look at the connection to the series. I'm using a partial sum function here. This is a cumulative sum function. So it's taking all the outputs from that list of indices. Maybe I'll go back and change this back from 50,000 to 500 so we don't have so many points. So it's going to take that list of indices from 1 up to 499 now, plug all of them through our sequence terms that we had, and then this cumulative sum function from NumPy is essentially a partial sum. At each position, it's going to add up all the outputs of the sequence before that, and I'll just plot those. So this is my sequence of partial sums. Notice we do not need the explicit formula for the sequence of partial sums, which is good because it's very hard to find. Maybe not even possible to find in this case. I don't know. I've not looked, but we can still get a really easy plot in half a second. And hopefully students can see, hey, we have convergence here as well. Not at 0, which makes sense because we're adding a bunch of stuff together, but we can see that this sequence of partial sums converges. We can get an idea of what that's going to converge to by doing that same trick that we did earlier. Let's just print off the very last partial that we plotted. And then we can go ahead and put a horizontal line there. So here's our partial sum, the very, very last one. That's the partial sum with 4,000 or 499 terms, I think it was. And it's 0.573, blah, blah, blah. That's a pretty good estimation of what this sequence of partial sums is converging to. That's a pretty good estimation of what this series is converging to, right? That's something that we normally wouldn't get to do too much with a Calc 2 class. Figure out specifically what these converge to if they're not these like nice known infinite series. There's lots of follow-up questions that we could ask on there. There's more plotting stuff for limits that we can do. Here's a function that we're going to take a look at this limit as x approaches 1. If you've taught calculus before, you can see, oh, this is just a derivative evaluated, right? This is the derivative of e to the x evaluated at 1. So we know what this is, but when a Calc 1 student is learning about limits, they don't. So I'll just build that function. Again, I have to use NP for the E constant, pull it from that NumPy package, and I'll set up a list of X values, and I'm just going to show you what this does. So there's like this weird error here, or a warning. There's an invalid value. That's because if we think about what we're plotting here, I'll print these X values out so we can see what they are. Oops, that's not how we type it. There we go. These are the X values that we're plugging into our function. -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. If we're plugging those into this function, we can see we're going to divide by 0 at x equals 1. So this doesn't really make sense from a limit standpoint, like in terms of anything that we're doing here. Getting only these points, that's not going to help us approximate a limit very well or anything like that. What we would like to do is use a lot more points so we don't have this like weird jaggedy line here. We want to not include x equals 1 because if we're thinking about limits, we're trying to have our x values approach 1 but not equal it, right? We want them to get sufficiently close but not equal to 1. We'd like to look at x values that are closer to x equals 1 than the ones that we have, right? We're a whole unit away here. That's not that helpful. And then maybe we'd also like to split them up into a list of left values and right values so we can think about one-sided limits. So this is where that arange function is really nice, because I'm going to now count by point ones. So this x left list is going to count from 0 up to 1, not including 1, by point 1. So it's going to be 0, 0.1, 0.2, 0.3, up to 0.9. And then similarly, my right list of x values is going to count from 2 down to 1 by negative 0.1. So it's going to count down to 1.1. And if I plot these, I added some lines on here and printed out those estimations of our right and left limits here where these lines are. We can kind of get an idea of where this limit might be. Now, we can do a better job by just changing our step size. So here, I've changed my step size to be really, really, really small. So this is going to count up to 0.999999. And on the right, it's going to count down to 1.00001 here. And we'll just do the exact same thing. We get our approximations. We can see, hey, that's looking pretty close to E, just like we want. Everything looks pretty good here. Also, I like this because we can talk about epsilons and deltas with limits. Our step size, you can think, this is really representing delta here in our epsilon delta definition. And we're visualizing epsilon getting smaller and smaller and smaller by these red bars collapsing on each other. So this gives me a lot of nice room to discuss epsilon delta definition of limits with students. Here's a piecewise function. You can look at this later. I don't want to take up too much time with all this, but we can do the same kind of graph here and show like, hey, look, the one-sided limits don't go to the same thing. We're not able to find, y values that are within some distance of each other that's better than this epsilon, whatever, blah, blah, blah. So hopefully we can see like, yeah, that limit's not going to exist. A lot of room for asking follow-up questions with students there. Integration is fun. Like I said, I like giving my Calc 1 students this Riemann sum to construct, sine of x squared, because that's not something that they can just use the fundamental theorem of calculus easily for. So we'll build the sine of x squared function, and we'll just plot it, see what it looks like. There's no axes on here, which sometimes is helpful, sometimes not. To do the actual Riemann sum, we need a couple of things. We need a number of rectangles. We need to construct delta x. We need to go ahead and come up with a partition of x values. I'm going to use a left partition here, and then we need to build the actual Riemann sum and evaluate it. So I'm going to start at 0, go up to pi, because that was my interval. I'm going to split this into 10 rectangles for now, just for fun. Here's my calculation of delta x, just the way that you would see it in a textbook. I'm going to use this NP arrange to build my left partition, because this is going to count from 0 up to pi by delta x. And this is kind of nice. It doesn't include pi here. So this is really going to be the leftmost points in this partition that we have. And then we can plot all this stuff. I'm going to put these bars on here. This is going to be my Riemann sum. And there it is, a left Riemann sum with 10 rectangles. And there's our approximation. And then the question that students always get asked is like, how do you make this approximation better? Or how does this become a definite integral? Well, it's when n goes off to infinity, right? And we look at the limiting value of this Riemann sum area. So let's just approximate that. Let's look at 100,000 rectangles, and we'll just repeat the code. It's going to take a little bit to run. Maybe I used too many, I don't know. I always ask students like, what are the drawbacks from doing really, really, really good approximations? And this is the answer. It takes computational power. Because I'm lazy, I'm going to stop it and I'll try it with a smaller number. Let's just do 1,000. Okay, now it's going to restart, so I got to go reload this. I got a little greedy there. My eyes were bigger than my stomach. So here, do I have my function defined? Not yet. There, I just have to rerun this stuff. And now with 1,000 rectangles, it should do an okay job. There we go. Look at that. That's essentially just shaded in, right? Those rectangles are all so small that you can't even tell the difference. So this is probably a pretty good approximation of that integral. You can look up what that integral is. I don't know. In my Calc 2 class, I make them do the same thing, but with a Taylor series version of this. You can walk through all the calculus work here. I'm just finding the Taylor series for sine of x squared and integrating it, between 0 and pi. There's a 3 in there for some reason. And so this is the sum that we end up needing to evaluate. That's what that integral is, right? And so here I'm just going to steal a factorial from this other package, because it'll work that way. I'll define a terms of this series here, and let's just add up a whole bunch of them. I added up to 154. Remember, it doesn't include 155 here, because any more than that and the factorial gets too big. It gives me an error and it's like, oh man, I can't even deal with this. The factorial is too unwieldy. So this is an even better approximation of that area that we were looking at above. It's fun to make students talk about all that stuff. Maybe we'll make them do like the alternating series remainder theorem here to get a bound on this approximation, and then they can show that this is better than the Riemann sum approximation. There's lots more that we can do. I'm not going to go through the Newton's method because we are running a little low on time. But maybe I'll just show you what it is. I built a Newton's method function. There are better ones out there, but this is a fine one. We're going to do an optimization problem for this function here. It's a terrible function to do by hand. I need a derivative and a second derivative because I'm really looking for critical points, and that's the thing that I'm going to use Newton's method on. So Newton's method is going to have an initial guess and do some stuff, and this is the approximation of the location of that critical point. And then I just did the second derivative test here on it. I got a positive second derivative, and so that means that it's concave up. This is a minimum here. And then there's some more work that you can do, but we're running out of time. So I want to come back here and yeah, you can play with that more if you want. There's a link in there. Feel free to grab that and dig through it if you'd like. What have I learned from all this? I've been doing this almost a year. What's going on? I've got a couple of takeaways so far. The first is that managing student anxiety is like the most important thing here. It's super essential because that's the big struggle point. The students aren't going to struggle with the code as much as they're going to be anxious about struggling with the code. And on that note, the coding, I don't think it really matters if the student doesn't understand calculus. So I'm trying to make sure that calculus is the focal point here. And so I will give answers away for the coding side of things. I don't care so much about that. I'm good with them collaborating on it because I really want them to be focusing on understanding the calculus and not just the code. There's tons of cool things that you can do. Lots of cool packages and libraries that you can use in Python to do lots of cool problems. And so I found that I spent a lot of time making decisions about how I was going to approach the kinds of problems that I wanted students to work on. And then the other thing that I've noticed is that I'm really bad at writing detailed lab instructions. And it's really hard to do. Even with what I think are great and detailed instructions and examples, I'm still constantly tinkering with them, finding issues with them, finding students that are misinterpreting them in ways that I wouldn't have imagined, finding that students' anxiety will make them misinterpret stuff. And so I spend a lot of time re-explaining the tasks that they're supposed to do to students, and I'm okay with that. That's just a decision that I've made that I'm happy doing. And then when I was going to start this, I went to a bunch of talks on using technology in classes and labs and stuff like that. And everyone said, oh, it's so hard to start. And that's true, but it was actually easier than I thought. Once I got a little bit of momentum, I felt like once I could figure out from a big picture how I wanted to approach these labs, things kind of fell into place. It's a lot of work thinking about how I wanted to structure them and what I wanted to do. But after that, I'm at a point now where I can write a new lab in a day and be happy with it. It might not be perfect, but it's something that I can give to students. Because I've thought about like how I want to approach it all already. A couple of things that I wanted to keep in mind for the future. These are mostly notes for myself. Sage math is cool. It's like Python with some extra stuff. And from what I can tell, it makes it look like Mathematica kind of. And you can do some of the same kinds of things that Mathematica can do. And there's some really neat implementations that you can use into Canvas or Blackboard or other LMS that you're using. Where like I might be able to make this a part of a quiz where students could type in some code and run it and get some answers and then include that as an answer in a quiz, which would be super cool. I haven't made use of retakes or corrections on these yet. I'm interested in how that might work. Right now, I just post the solutions as a PDF. For most of the other stuff in my classes, students can retake things or do corrections or whatever. So I'm interested in seeing how that might work on these labs. And then I'm working more on pushing this towards mastery grading. And so I do want to focus a little bit more on the discussion responses and make sure specifically that those are connecting with like actual course outcomes in a really obvious and transparent way. So those are some of the things that I'm going to be thinking about to kind of expand this in the future. But that's all I have. If you have questions or anything like that, I would love to chat with you. At the beginning of those slides, there's my contact information, so feel free to let me know, or we have maybe a couple minutes here. I don't remember when this is supposed to go till, but I can take any questions that you've got.
Thanks, Peter. I was wondering, I really enjoyed all of that, and it's exciting to see what you're doing, and I'm sure you're really enjoying that learning process and being stretched and challenged yourself. You know, I like doing things like that. But I was wondering, you know, I've never done anything with Python. I've just done a few things with LaTeX, or however you say that. And so how did you like get the ball rolling at the very beginning with Python?
I went to a talk at IMACC in Milwaukee last year, and somebody shared like 2 of their labs for Calc 1, I think, and it was written in Python. And that gave me a really clear like view of like what the code looked like that they were looking at. So it gave me a start on like what I should be Googling to how to do certain things. And so that was helpful. And then outside of that, it was mostly like once I had a handle on some of the little kind of like main important things of code, it was a lot of just like looking around and trying to figure out what kinds of tasks do I think would be useful to do. Most of them, you can see they center around making your approximations better, which I think is like the main theme of calculus anyways, right? Cutting a problem into small pieces and using an approximation and then limiting that. So I tried to figure out what kind of tasks I wanted to do that fit those themes. And then you'll notice if you look through them, I pretty much hit the same kind of code. After like 2 different tasks, you'll realize that most of it is the same kind of thing.
Yeah.
I'm just increasing some endpoint or making a rectangle smaller or whatever. So I started kind of small on that side. I haven't looked too much at other cool things, but there are tons of cool stuff out there that I just don't know enough about yet.
That's great. Thank you.
Thank you.
A question.
Yeah.
Have you considered using this type of approach in any other courses?
Right now, so yes and no. For the past year, I've tried to focus on not taking on new courses because it's terrifying to build a new class online, at least to me. And so I've only focused on putting them in the classes that I already had built. But I'm trying to get more into teaching some stats and maybe some other types of courses that fit like some data science background stuff. And so I'm definitely going to introduce them into my stats class in the fall. And I feel like now I have a pretty good idea of how I can do that. I'm interested to see how it could fit into a differential equations course, although
Yes.
I think I might have to use things more like SciPy and stuff like that would kind of get things from like a Mathematica viewpoint, because I don't know if I could hard code much of that myself. I don't think I'm talented enough at coding, but those are the other classes I've thought about.
Yeah, thank you.
No problem, James.
Well, I have a question. It's the same kind of question I have whenever I encounter any cool idea like this, and that's time.
Yeah.
The perpetual enemy of higher ed faculty everywhere. So I guess, how many of these do you do in a typical course?
Yeah,
how
good
much
question.
time do you allocate to them?
Good question.
And how do you make that work in the grand scheme of the course calendar?
Yeah, I meant to put that in my talks, like slides somewhere, but when I set these up, I knew I did not want to include a lot of these labs at first, partly because I didn't want to write a lot. I didn't want to have the responsibility of having to create a ton of assignments. And also, I wasn't sure how students were going to do with them. I wasn't sure how long that was going to take. So the first time I did it, I think I did 3 assignments all semester. And one of them was the one without any calculus. So there was only 2 actual labs that had calculus on it. I felt like that took me a decent amount of time to write. But like I said, now that I've done that, when I created the labs for my other calculus course, I forget which one I did first, if it was Calc 1 or 2. I think I did Calc 1 first. But when I created the labs for my Calc 2 course, they went way faster. I have 4 labs in each class now, and I feel like that does a pretty good job. I might introduce 1 more in Calc 1, but I feel like the way that I've got the topics split up in Calc 2 is reasonable. I try and give students a decent amount of time to work on it. because there's only 4 of them, I mean, I put the labs up at the beginning of the semester so they can see them, and I try and refer to them as we're learning topics. So like when we learn about improper integrals, I tell them like that you can start working on this part of the lab now, because we know everything we need, even though there are some sequences things on the lab and series stuff on the lab, right? We don't know anything about that yet, but start working on that. I dedicate a lot of my office hours to working on these labs with students. And right now, my Calc 1 classes are all hybrid. So I have face-to-face time with students. So whenever we come up to a due date, I tell them, you know, bring your laptops into class, because I'm not able to reserve lab space right now with COVID stuff, but bring your laptops into class, and I'll put the lab up on the screen and spend time working on this with each other, doing the code parts of it. That's been really helpful to cut down the time that students have to spend. If you want more specifics, we can talk after about how long it might take to write them, but.
All right, yeah, so I guess I was thinking more about in-class time, and
Yeah.
it's sounding like there may not be a whole lot of that based on if I'm interpreting what you said correctly.
Most of that is due to just the nature of how classes are running at Morraine. I only have 2 classes that I'm able to meet with students on. I meet with each student once a week. And so we just don't get a lot of face-to-face time. In the fall, I will have more face-to-face time with each of my students. And I'm planning on dedicating some class days to just going through those, especially near the beginning of the semester, to ease some of their anxieties about what those look like. Thanks. Any other questions? All right, I think I put a link to my GitHub in there. If you want to see that, all of my labs are on there. And when you click through them and find them, there should be, like when you open the labs themselves, there should be a button on the top of them that says like open in Google Colab. So you can open them up and play with them and stuff like that. And then on the slides, there's my email address and my Twitter handle if you want to connect with me there. Thanks so much for coming, everybody.